Welcome to the project review for the Battery Energy Storage System Optimization and Peak Load Shaving Project. As part of Clemson University Senior Design 2, we are Team 1 in the fall of 2022 is being prepared for Dr. Hassan Raza. Our team includes Caitlin Casey, a computer engineer and a software lead on the project, myself, Jacob Hauser, electrical engineer and project manager and our reliability lead, and Daniel Sabion, an electrical engineer and our data processing lead. Our advisors for the semester include Dr. Johan Enslin and Dr. Hassan Raza from Clemson University, Dr. Drew Clark and Mr. Steve Wisnant from Duke Energy, and there will be a future team to take this over in January of 2023 for the continuation of this project. A big thank you to Duke Energy and the Center for Advanced Power Engineering Research. They are the sponsors for this project and the primary motivation. The problem set behind it is that there's an increased utility adoption of grid-scale lithium-ion batteries, and these require optimized control schemes that can balance the cost savings from energy arbitrage, the health, and the lifetime of the battery, while also maintaining an energy availability guarantee. The primary problem here is that lithium-ion batteries degrade during their use. The average state of charge is the primary factor of this. The higher the average state of charge, the faster the battery will degrade year to year. Charge and discharge cycles also have an effect, but not as severe. So our goal is to create an algorithm that'll only charge the battery up when necessary. It'll maintain a low average while still employing the peak shaving component to make best use of cheaper generation and off-peak hours. But we're also maintaining a goal of 97% reliability in the event of a feeder loss. We can predict outages using weather forecast data, charge the battery ahead of time, and then deploy it in an islanding mode while repairs are underway on the primary feeder to keep a local area of load, keep the lights on for those customers rather than a complete outage. The future development will include a predicted load and photovoltaic generation using machine learning. The grid-scale lithium-ion batteries couple well with and are often coupled with solar photovoltaic generating sites due to their symbiotic nature. Our project components include a graphical user interface and display, an outage prediction algorithm, a peak load shaving algorithm, and future development includes the load prediction that I just mentioned. Caitlin will now just walk through the GUI and how it works.
When the GUI is run, a home screen will pop up with the title Battery Energy Storage System and the options to click on Predicted Load, Feeder Data, or BESS Data. So if I click on Feeder Data, a window will pop up with the options to choose between actual circuit kW, kVA, kVAR, current, and voltage data. So if I click on actual circuit kW, I will be taken to a window where I can choose between dates from January 1st to August 31st. So if I click on January 4th, data from January 4th will be shown for the actual circuit kW data. And depending on which button I chose, the data will be different. So if I chose circuit or voltage, the circuit or voltage data would be shown, and it would also differ depending on the date that I chose as well. Once I've exited out of all of those windows, I can then choose on BESS data. And the BESS data will be shown, and it gives the columns list, timestamp, mode of battery, and state of charge. And depending on the state of charge, the mode of battery will change. And the mode of battery can either be charging, idle, or discharging. You can see kind of briefly it goes between idle and discharging there, and then it started out charging. So then if I exit out of that BESS window, I can then click on predicted load. Clicking on predicted load then takes me to another window where I can choose between January 1st and August 31st data, just like the feeder data. So if I click on January 4th, taken to a window with the January 4th data, and this peak load data has not been created yet since another team will be taking over the project in the spring semester, and they have to incorporate a machine learning algorithm. So currently we just have dummy data, which happens to be the circuit KW data.
And to explain how the feeder outage prediction algorithm works, it's going to choose between 3 levels of risk. There's going to be a flowchart coming up soon that I can walk through. But the decision metrics for this are based on specific feeder outages, looking at a sample case from Duke Energy over the period of 2019 to 2022, identifying the weather patterns that were most likely correlated to the outages that occurred. But the output target for this is going to be a minimum state of charge. Like I mentioned, you're pre-charging the battery in event of a potential outage so that there is energy available to produce and keep the lights on for customers in an islanding mode while repairs are underway. It starts off taking in weather forecast data. It's going to look 24 hours ahead to see is there inclement weather coming up? Are there high winds, severe warnings, or low expected photovoltaic generation that could otherwise be used for the local area? Based on those, it's going to set a risk level. A low risk level is going to clear the outage target or let the battery operate in the most economical way. A medium risk will set an outage target minimum to 50%, while a high will set it to 80%. That will finally be output to the peak load shaving algorithm and incorporated into a pre-charged target value ahead of inclement weather.
Hello everyone, my name is Daniel Sabione, and I'm here to talk to you about our peak load shaving algorithm. So the algorithm starts by reading in the load data from the breaker and the point of common coupling recloser. This was all provided by Duke Energy, and we're mainly looking at the kVA and kW output at these two locations. And we use this to determine what the actual load demand for the feeder is at any given moment, given that this is minute by minute data for the entire past year. So we use that to determine the mode of operation based on the most recent 10 data entries in the program. And that basically decides whether we charge, discharge, or keep it in idle mode and do neither of the above. And we also have to stay between the state of charge limits given by Duke Energy. We don't want to charge it any less than or any higher than 90%, and we don't really want to discharge it any less than 10%, just because that'll affect the health of the battery. So here's the flowchart for the algorithm. Basically, like I said earlier, we read in all of the data, and then we read in the 10 most recent data entries and look at the minimum value in that 10-minute data set. And we want to see if it's above 200 kVA for the breaker output, because if it's less than 200 kVA, then we can basically assume that the breaker is offline and we're in an outage scenario. So if we then look if the state of charge is greater than 10%, and if it is greater than 10%, then we'll send a discharge mode signal until it is no longer greater than 10%, and that's when we would send an idle mode signal. So if it's not in an outage scenario, we want to see if the breaker output is greater than 2 MVA. And if it is greater than 2 MVA, then we'll do something similar to the outage scenario where we check if the state of charge is greater than 10%, and if it is, we'll discharge the battery, and if it's not, we'll send it to idle mode. If it's not greater than 2 MVA, this means that we're in between, or we then see if it's in between 1.8 MVA and 2 MVA, which is kind of the gray zone where we don't really want the battery the controls to do anything, because we don't want to waste energy and we don't want to overcharge for no reason. So if it is greater than 1.8 MVA, then we know that it's in between these two, and we just keep it in idle mode and keep it pushing until the next data set is read. But If it's not greater than 1.8 MVA, then we know that we're below that, and then we just see if the state of charge is less than 65%. And if it is less than 65%, then we charge the battery till it gets to the 65% threshold that we've come up with. And once it gets there, we send idle mode signal to keep it running like normal. And basically, once this is done, it will just keep reading in the last 10 data entries and go through that entire cycle again. So here's a visualization of exactly of what's going on here. The yellow is going to be the circuit demand, the blue is going to be the state of charge, and the red and the green are the separations of the modes. So we can see here that we are in idle mode since it's flatlined all the way until we get about 10 minutes worth of data above 2 megawatts. And once we're above that 2 megawatts for 10 minutes, the algorithm decides to discharge that battery. And it'll discharge that battery all the way until around right here where it dips under, and we get a little flat line, but it comes right back up, so it discharges again. But once we're in that range again, whenever we're in this 1.8 through 2 MW range, it'll flatline, but once it sees that it's 10 minutes above that, it'll go back down. And then till basically the rest of the day, it's going to stay in that idle mode till midnight, where it just creeps under and it starts charging again.